Welcome to the sharing of system inertia requirement with increasing RE and HVDC infit. It is part 1, and here is Caroline, who is working as an electrical engineer on power system planning. There is increasingly many people asking if the increasingly large amount of penetrations on RE and HVDC will cause any problems on frequency stability because of the reduced inertia. This is their problems, and this PowerPoint is to share with you what would the other utilities do to avoid this kind of problems, or is there any problem if there is reduced inertia. So with the increasingly many non-synchronous generation, which is PV and wind, and HVDC in wind, system inertia is reduced. So, what is system inertia? System inertia is actually the generator KE. Just think about the moment of inertia that we have learned in university. When there is a rotating mass, the system KE or system inertia is equal to half J omega square. And we try to normalize it with a constant, which is the rated power of the generator, and it is the inertia constant. We found that if the system inertia is dropping, it increases the frequency nadir and Volkov. Frequency nadir is the minimum frequency that occurs in the system during a frequency event. And Volkov is the DFDT. Volkov means rate of change of frequency. You must notice that the frequency drop is due to the change of power, or actually the energy deficiency. And which is this area. Okay. And this kind of increasingly large frequency nadir and Volkov because of the reduced inertia results in cascade tripping, which is due to the under frequency relay. Failure of under frequency load shedding scheme, which is due to large inertia, and the Volkov relay cannot help to detect, or the frequency is dropping so fast such that the system cannot react, or any kind of equipment failure. So the problem is how to estimate system inertia, or how does the system inertia concept relates to the frequency. And then we try to talk about how to provide enough system inertia, or what is enough. And in the end, we talk about what is the limit of system inertia. Is there any bifurcation points that once the system inertia drops below that limit, the system will be unstable and it will cause some kind of big problem, just like a cascade tripping, blackout, and so on. And what is the effect of inadequate system inertia? It may not be a problem, but we try to emphasize it is a problem because we haven't faced these kind of problems. So let's look at the figures on the right. So as you can see, there is some kind of frequency event. The frequency drops, and as highlighted, the first area in blue is what we call the arresting period. We try to fill it up with the inertial energy. And it is noted that Ke is half J omega square, and delta Ke is actually J omega, which means that with increasingly large J, or more and more generator, thermal generator, synchronous generator, we need larger KE to change a delta W. Just like here, if we have a larger J, we need more energy to change delta omega, which in turn tells us that if there is a larger generation, there is larger synchronous generator connected to the grid, the frequency will not drop so fast, because for the same power discrepancy, energy discrepancy, the frequency will not drop so large. And here you can see that the purple part is the inertial response, because once there is frequency drop or there is a discrepancy in power, the generator will try to release some kind of kinetic energies and drop the frequencies to fill the energy deficiency. Then there is another term called primary frequency response, which is the governor response on grid. So the first one, inertial response, is to arrest, mainly arrest. And the second part, primary frequency control, is to rescue the frequency drop, which is to fill up this part, to push the frequency back to the normal frequency. So let's have some kind of case study. Air grid, which is the island case, it has some kind of rules written down, or policy written down. At most 1 Hz per second roll-off and the inertial flow of 23 gigawatts are provided with minimum number of largest synchronous generator on bar or minimum generations. So you can see that first, there is a limit on roll-off, and there is a limit of inertial flow, which is the minimum inertia. And what is this in terms? It is talking about the minimum number of generator or minimum generation. It's not talking about the maximum. We do not need to have some kind of limits on the maximum generator on grid, because it's not what we concern. And the only concerns that we put so much generator on grid is about money. So, as illustrated in the figures on the right, the black line is the inertial value in the field mix or in the generation combination. With all the wind turbines, all the PV connected to the grid, from 0% to 1% on, such that it is connected to load and generate, and we observe the inertia. And this is the result of 2020, and this is the result of 2030. It means that there is increasingly many RE on grid, such that if we try to decommission the thermal power plants, and that is all left with wind power and PV, then there will be decreasingly trend on the inertia. So what's the concern? The first one is the frequency stability. We've got reduced inertia with, of course, with HVDC infit. We may not have so much RE, but we have got many HVDC infit built and much HVDC power infit to our grid, which means that the thermal generator, although it is not decommissioned, it still be shut down because we don't need that. And if the inertia is reduced, the roll cost is increased and also delta F is also increased, which means that if there is a frequency event occurs, before we have got the blue line and now we have got the green line with increasing the FDT and also the minimum frequency. The second one is that with increasingly many HVDC infit, the local generation is reduced. It also means that the reactive power reserve, which includes the excitation of SynGen and also reactive power source, such as capacitor or reactor, if you consider negative power source, will reduce, but we talk about it mainly on the excitations on generator. The lack of local dynamic voltage support and system reactive power scarcity at the recovery stage will be reduced. Let's note that first, this is local because voltage support requires more reactive power at local stage. Just consider transmission network. If we want to push P plus JQ to the right, it's much difficult to push Q because the X is much larger, and hence it's better for us to install some kind of devices to provide local support. Second, it is about dynamic support because it is all static. This static capacitor installed, we can't have control. Even we have control, it is still step control. But if it is a generator connected to the grid, we can tune it by providing flux to it, and the flux is controlling the reactive power. So the flux can be controlled and the support can be dynamic. We can just see how much the voltage drops, and we try to provide it with more and more flux. So here is local dynamic voltage support and also system reactive power scarcity as a recovery stage, because once there is a fault, we drain out some kind of reactive power because of the fault. The fault point is always having reactive power from the fault current because the system is highly reactive. So if there is a fault over there, the power drain out is mainly reactive. And once there is a restore of the system, the reactive power is used to build up the field and also effective power transfer, like the charging current or transformer magnetization. And that's why in the recovery stage, we need to absorb so much reactive power, and there becomes local scarcity. So here is what we concern, and here is the standard in air grid to bound the amounts of generator on grid such that excitation can be provided. There is not much problem about the critical inertia and also voltage stability. So what if there is some kind of inadequate inertia problem occurs? here comes 4 solutions. The first one is, of course, if we could, we provide more inertia to the grid. Basically, the inertia is from rotating mass. If we have more and more rotating mass connected to the grid, then that will be okay. How come there is rotating mass? Just think about the generator and load. But one thing is called the condenser. Condenser is that we don't have the turbine, or we have a turbine with no load, which means that we don't blow it with steam. Then it keeps rotating and generating reactive power according to the excitations. Just let's see the figures on the right. It is the famous V curve of synchronous motor. By underexcited or overexcited with field current, then we can have different armature current and actually the load. Full load is 100% load, just like 100 megawatts, or no load, 0 megawatts. By having different field current, we can actually control the amount of reactive power, just like this is cosine phi equal to 0.8. It is also cosine phi equal to 0.8, but it is capacitive because we are overexciting it. We are generating reactive power. This is generating reactive power. Just by a synchronous generator moving with no load, then we can provide this kind of voltage support. First, it is voltage support. Again, it is dynamic voltage support because we can control the flux. Here, we can control the flux, and it gives the reactive power, which is a function of flux. The second one is increase the system strength. System strength is another term for fault level or for current. How much fault it can provide. Notice that it is often that we try to model a source with a source impedance X. Once if the source impedance X increases, the fault current IF reduces. If we could provide one more generator on bar, this is the bus bar and this is on bar, then the equivalent source impedance will be by half if the source impedance of the two synchronous generator is the same, then it's by half. Anyway, the source impedance will be reduced and the system strength will be increased. And in the past, the reason why we generate this kind of synchronous condenser or try to use it because we try to provide dynamic support to the grid. But now we try to include it because it can provide inertia. But it is noted that you need to start it up anyway, which means that you still need to provide it with startup costs. Later on, we have got a number on how much reactive power it generates or how much inertia generates and what is the cost. But one thing I must notice that the inertia is just 20% of the synchronous generator because the generator in the past is connected to the turbine and the steam blows and the turbine turns with the generator and hence there is inertia and there is power. But now it's often that the turbine is removed and hence there is only 20% of the J left, and hence the system inertia is actually reduced if we put a synchronous condenser instead of a synchronous generator. It means that anyway, if we could put more and more generator on grid with minimum generation, then it will be better. The second one is fast frequency response. Fast frequency response normally talks about the battery energy storage system, BESS, or the HVDC. Battery energy storage system, anyway, it is called an energy storage, can provide fast response to the grid to fill up the energy discrepancy. Just remember the frequency line here. If we want to arrest the frequency drop, we need to fill up the energy discrepancy or deficiency here. Where could we provide this kind of support? The first way is to provide it with a battery. The second one is to increase the HVDC input. This is noted that the problem still stays here because we don't know when should we trigger this kind of fast frequency response, because it takes time to measure the frequency and also it takes time to detect, which I will talk about it later. The note is that the synthetic inertia emulations and also virtual inertia cannot fulfill inertia requirement because it's not an inertia anyway. What we mean by synthetic inertia is that in the control loop of battery energy system or ROE or HVDC input, we actually include a block, which is a JS square or something like that. You can have something like a S square B S plus C, and you can have it tuned. It is to reduce the weight that the energy set points, or actually the voltage set point, that it changes slowly. And in the end, the response will not be so fast. But again, I must emphasize that battery system will have its problem. Just imagine there is a battery. It is connected to the system, AC system. Imagine it includes the virtual inertia or synthetic inertia, but the battery is so slow that it cannot arrest the energy because it's released so low. It cannot provide any fast frequency response, and in the end it becomes slow frequency response. Just like what is left is the primary frequency response from the governor. Just remember the governor is a speed controller from the generator because it provides fuel to the generator. And it's often that we try to model frequency events with governor turbine model and also low frequency dependence low, because it is all about the frequency and also the power relationship. The third way is to include some kind of grid forming converter with frequency power drop. It is to control the power flowing into the grid according to the frequency, the system frequency. If, let's say, there is a 10 megawatt PV, we notice that the frequency is 50 Hertz. Then we try to deliver to the grid like 8 megawatts. And if the frequency reduces, then we try to generate more to support the grid. Then it is grid forming converter with the drop control. But notice that it requires power reserve control, which is to reserve the power with the IV curve. This is MPPT and that is FPPT. The harvest power is this way, so that there is some kind of control or reserve which can be provided during emergency. The last one is very simple or very straightforward, is to curtail the amount of inverter space resources, which is the PV and wind. Once it is curtailed, then the load must be supported by synchronous generator on bar, or we need to simply turn on more and more synchronous generator to fill up that power discrepancy. So from here on, you can heard that we have got different kinds of frequency response components. Just like what I have mentioned, the inertia, fast frequency response, that is the third one, fast frequency response, and the primary frequency response. So here's all records in the figure. The inertia KE, system KE, cannot be fully provided to the grid because once there is a rotating mass, have all the kinetic energy provided to the grid, then it will not spin and the frequency will drop so large. It means that the actual energy that we can obtain is that part. And actually the inertia that we can obtain is in this kind of shape. We have got a term called effective inertia, which includes all the relief from the low relief, which is if we want to model a low power, we often write it in the form that is the functions of voltage and frequency. If the frequency drops, it's often that the power drops as well. Just think about a motor. If you want it to spin faster, then it takes more power. It's often that the power form is a quadratic. The curve is actually quadratic. Once, if you want to have faster frequency, then the load is much faster. Then synthetic inertia, which is to decrease the weight that an RE responses through the set point. If there is DC cap in the system, just like we have got a RE, a PV with DC-AC. This is often before we put DC-AC, we put it into DC-DC and try to put it in DC-AC to the grid. There is a capacitor here, the DC link capacitor, and once there is some kind of emergency, just like a power discrepancy, we try to remove the charge to the grid first. The voltage will drop, but anyway, we try to store it later from the PV. It also explains why we can provide more power during system emergency, but then we will have power drop because we need to restore it from the PV. Then another is the relief from inertia, which is the KE. Then the combinations of these three forms a term called effective inertia, because anyway we can't know what is the effect of the inertia on grid, because we don't know how much motor is plugged onto the grid. We don't know how much PV has the functions to provide this kind of voltage or frequency support to the grid. But all we can know is the inertia constant H connected to the grid through the synchronous generator we have. The second one is fast frequency response. Again, it is the extra energy sources, BESS, the energy storage. Note that the energy storage, you need to notice two terms, which is the specific energy and specific power. We want some energy storage that can provide large specific power, such that the system can react fast and release more power in a short time. It's often supercap, or sometimes it's called ultracap, or flywheels. The second one is HVDC with EPC. EPC is emergency power control, which is to release more power, to transfer more power during an emergency. Just like there is a tripping of generators and there is a large discrepancy of power deficiency, then we try to import more with HVDC. But what if the HVDC shuts down as the single largest in-feed lost? Then it will be another case that you need to support it in other method. So the fast frequency response is to provide fast enough response, of course depending on the system need and technology available. The concern is, the first one is, how long does it turn on? Sometimes it is about 0.25 seconds or 0.5 seconds. It is shorter than 1 second anyway. The second one is, how does it be triggered? It is a big problem because in a short time we can't differentiate if it is a frequency event or it is a fault with correct here. It means that the fault is cleared anyway, you don't need to do anything. Just like there is a cable fault, but we have got enough transmission capacity, but anyway the system will have some kind of frequency fluctuations, but the system can recover itself. You don't need to release. If you release so large, it's like you have got a 100 megawatts capacitor or 100 megawatts battery, and you suddenly release it, then it will be a big problem because there is some kind of power deficiency and it becomes over frequency. The third one is step or drop response. Just imagine you have got 4 times 100 megawatts cap. Then all you can choose is 4 step. But if you have a 400 megawatts sink condenser, then you can choose the amount of reactive power or power can be supported to the grid. Inertia can be supported to the grid. So it's all about the technology that you have or you can provide it. The fourth one is the time that the system can provide full response. Just imagine you have got a system just like a battery which can respond after an hour, then you can use it for nothing because it can't support anyway. If you need to wait for 1 hour to support it, then the system will collapse and black out. And the last one is the duration, just like I want to support it 15 minutes or I want to support it within 1 hour durations, then it is your choice and you can procure it, you can construct it and own it. And it is the fast frequency response. And the last one is the frequency containment response, is often called primary frequency response. This is the term that we have used in power system, and some foreign country uses it as a frequency containment because it contains the or rescue the system frequency back to normal frequency. Then it is actually sized to tackle the largest secure loss without load shedding, which is what we call the spinning reserve. And the second one is the time that we need to trigger it and try to obtain it, the durations that is to provide full response. And it takes 10 to 13 seconds to do it. Just like as shown in the figure. If you have inertia, then there is no delay. But we notice that there is decreasing inertia. This is some kind of suggestions to tell you that you need to have synchronous condensers. In the end, synchronous condenser takes a large startup cost and you don't want it, then I can procure some kind of fast frequency response. We have more than 1 second delay, which is to arrest the system frequency drop. But sometimes you may not want some kind of power electronics on grid, or you don't have some kind of batteries on grid because battery needs maintenance, and this life cycle or cycle life of a battery is just 10 to 12 years, then it will be a problem. You don't want something connected to grid with so short cycle life. Then you may have some kind of primary frequency response, which is basically the synchronous generator on grid, or other synchronous generator on other grid, which is interconnected to your grid. But the response will be 10 to 20 seconds. One thing that I must emphasize is that the primary frequency response is often from the governor, and he is the small figure mentioning what is governor working. First, the system is rotating in the system frequency, and it actually gives a flux, or it is a screw that connected to the governor, and this force will push this lever to the left and try to release. This is the door connected to the steam drum or the steam pipe connected to the turbine. It can control the door simply by means of the system frequency. But of course we want to have some kind of control. That's why we have got the spring to dam the opening, and also we have got the screw to provide some kind of control on the minimum or maximum opening. Just like the minimum is to close the whole valve, and full response is to open the full valve. Then it is the frequency response, and the droop is like that. It is often a 4% droop. And the group is about the relationship between frequency and power. The system takes the frequency and drives the governor, and this is the primary response. You can see that there is some kind of deadband effect, which is if the power output is in full or just in about 0.5, then you can set a deadband which provides no moving on the governor. So the next problem is we have talked about so much on inertia, the inertial product, and the next one is we want to know about the limits, and we want to know how is it measured. Because if we want to know the limits, then we need to know how it's measured and how to take some kind of response to it. So there are 3 ways, and actually 4 ways, you may say. The first way is to know the synchronous generator or condenser on board. It's not that the J or the H, this is the inertia constant or the moment of inertia of the generator. It is all mentioned in the nameplate or from the commissioning report. And by using these kind of equations, you multiply the rate output with the inertia constant, that is about the system KE, and try to sum up all the generators KE, then it will be the system KE. It's a simple method because it's all about what you know, but the problem is that there is some generator that you may not have the constant, or there is some kind of motor connected or some kind of load which is responsive to frequency, then it's all you don't know. And that's why we try to use some kind of what we can measure. There may be some kind of fast frequency measurement, like high speed frequency measurement, and there is some kind of historical event. We try to take out this kind of data and try to do some kind of analysis on the system inertia. Then we can use the string equation base. Just remember the string equations. We try to have some kind of calculations just like that. Then we try to generate these equations, and these equations is actually measurable, all the terms. This is the Volkov. The actual change of the power, the rate of frequency. By having these kind of measurements, then you can have the system kinetic energy. But here is the factor affecting its accuracy. The first one is the windowing of Volkov. What do we mean by window length? Yes. Just imagine we measure the Volkov of this curve. You can take sample of these two. You can take sample of these two. Or you have got a faster value. Each line has a different Volkov. Or should we take an average of it? We don't know. That's why the windowing of Volkov affects its accuracy. You can see that it is over the Volkov, and if the Volkov is calculated in the wrong way, then it will be a big problem. The second one is about the start time of the event. You know frequency is actually fluctuative. Should we choose the time here or should we choose the time here? No one knows. And actually during the system disturbance, there is some kind of frequency distortions. Just like if I asked you to tell me what is the system frequency of this part, you don't know, because if you think about frequency, it is often like a sinusoidal. A system is sinusoidal, then there is a frequency. But if it is not a sinusoidal, just like it is a step, what is its frequency? You don't know. You can't say what it is. And too much worse, you don't know when does it ramp up. Then it will be a big problem, right? The second one is about the power measurement. If you operate in 1 megawatt to 1 megawatt, maybe, it's difficult for you to measure the low power during fault because it actually is noisy. It fluctuates and you don't know, you take an average or what you should do. The fourth one is actually the inertia chain. Remember we talked about generator tripping. Once the generator is chipped, the inertia, the system KE, actually changes. The fifth one is the load damping effect. We don't know about what is the load that is connecting to the grid, and we can't know how large is the load damping effect. And the sixth one is the low frequency voltage coupling, which means that, as I have said, we try to model the load with the quadratic equations. But no one knows how does the voltage and frequency interact. We have got equations here to talk about the load damping effect. How does the change of the frequency affected by the loss of the power and the on-bar load. So it's about the string equation based on what you have measured, what the whole system interactions. And the last one is about the power modulations. If you cannot know when the event is starts and how large the Volkov is, then why don't we create something that we know? We try to modulate it with a power sinusoidal. Just like the average power that you need to transfer is, say, 5,000 megawatts. We try to add it up with a 10 megawatt sinusoidal. By tuning that, we can actually know the change of frequency, just like we try to have some kind of frequency change, or we may not have it, but anyway, we can just do what we want. But the problem is actually existing because no one knows if it occurs the same performance or it is the same inertia during the faults that we have concerned. What we call the term that we mentioned is the data asymmetry problem. We don't have the data on the faults that we concerned. The fourth way, if we talk about this, is the first, the second, and the third. Then the fourth way is to use some kind of machine learning skills. But again, machine learning skills actually has the problem of the aforementioned measurement-based approach. So here is the frequency response requirements that occurs or used in different synchronous area or other utilities. The first one that we need to concern is the inertia overload value. This is often a value provided in different utilities, and it means that if there is an increase of load, then you need to have more inertia because this delta P can be large. Then the inertia must be large to fill up the delta P. The normal value is 3 to 5.7 V for REE and 5.7 for the Manitoba Hydro, which is other company's synchronous area. The second one is about the primary frequency reserve, which is depending on the drop. We write it in a drop form plus a dead band, which is the frequency power or power frequency form. It is sized based on the single largest in-feed contingency. In Hong Kong, we try to use it with the largest generator connected in the interconnected grid. But in the future, it may be HVDC in-feed failure because we may have all the power in-feed from the HVDC, or it may be the single largest generator again on our grid, just like a wind turbine, just like a PV system. We don't know. It depends on the fuel mix and also the generator combinations, or it will be the nuclear power plants. No one knows, but it is the single largest generator or single largest contingency that we need to consider. It's often that it is about the inertia to arrest the Volkov and also minimum frequency. It is about the inertia, but another thing is about the constraint violations. Just like if we have got only two feeders connected to load, once if I have a cable tripped, then the ladder cable cannot take so much power from the generator to the load, and it will be a problem. Or the generator cannot generate so much power to the load, and it will be another problem. The power is a problem itself, and the inertia is another problem. You can't mix it up. The second one is about the percentage of load. It means that how much load on the grid, and if there is some kind of reserve that we need to share. In Hong Kong, we try to share with another utilities and also the utilities in the mainland, which is interconnected. It is also the reason why we try to interconnect with other power system. But it is also a problem that once the system is split, we don't have enough spinning reserve on grid. That will be a big problem. So the last one is about the fast frequency reserve products. Just to tell you several product in other utilities. The first one is COT, which is utilities in the US. They provide two plans, Plan A and Plan B, just like you buy McDonald's. The start time is 0.5 seconds or 0.25 seconds. You need to endure the power frequency drop for 1 hour or 15 minutes. It depends on what you buy. Just like if I have got a battery and here's the grid from COT, then I can sell it with Plan A. Once if it drains out my battery's power, it need to pay for me. For AEMO, it requires 2.55 megawatt second inertia. Remember, it is kinetic energy. It must be power times the time per MVA installed capacity. I should highlight this term. Installed capacity, but not the actual power generated. It means that if you turn on the generator on bar, no matter how much power it is generated, you must have 2.55 megawatt second inertia per MVA of the installed capacity on bar. Yes, only provided when the unit is generating supply. I may emphasize that the generator can be used as a condenser, but it is still connected to the grid, just like a generator with zero supply, but it is still supplying. Then you still need to consider it, but I can prefer you that the generator can be operated as synchronous condenser such that the KE can still be kept. The last one is that if you have got a generator, look, that it is not about synchronous generator, it is generator, which means that you can have a PV or wind or thermal, which is synchronous generator. Then you can have the options to trade off inertia with fast frequency reserve, which means that this requirement is for the generator larger than 10 megawatt, which means that I have got a PV with 100 megawatts. I still need to provide this kind of inertia, no matter what I do. Just like I can do it with battery support, providing fast frequency reserve, or I can have a synchronous condenser supporting the PV system. We can have a synchronous generator operating as synchronous condenser to absorb reactive power to control the voltage. But anyway, it is on bar, that's why it can provide KE. And the E-grid provide dynamic response to track the frequency. Look at that. That is the requirement. 10 steps. It is in step form, and the step cannot be so large. And another requirement is the static capacity. Drop in droop, recover in constant. If the power drop, you need to provide power, or the frequency drop, then you need to provide power in drop form. And if the power starts to recover, then it will be constant. This is recover. And the last requirement is static capacity. Once there is a set frequency, it reaches frequency set point, just like if there is drop and the frequency is here, then you need to provide full response to the grid. Then it is the requirement for the frequency response requirement to the E-grid. And this is the last page on the part 1. E-grid or AEMO provide some kind of minimum inertia level. Just as a recap, we have talked about what is inertia, what are the types of frequency response that we can provide, and how to measure it. And now we tell you about the minimum inertia level that you need to cap. The first one is E-grid. It tells that first, you need to have some kind of limit on the largest infit and powerful to our inertia shortage area. Just say it is the inertia shortage area. It must provide some kind of local generation because the power flow is limited and the largest infit must be limited, which means that we can have several infit and also local generations, but we try to limit it such that once if there is a single failure, the delta P is also limited, or delta P max. So E-grid says that minimum inertia level is set to ensure the Wyckoff limit after the loss of largest single infit. It may be HVDC line, it may be a generator, but the DFDT must be limited. It cannot drop so fast. AEMO says that they will review it annually on the system security and also maintain the frequency standard, which means the F mean. Normally, the power system planner will have a minimum and maximum frequency requirement on grid, and it is a nominal frequency, and it cannot drop so low. It must provide enough inertia or fast frequency response such that the system will not go into under frequency load shedding or other kind of system protection such that the load may be shed or maybe some kind of larger interventions will occur, or else it will become blackout. EMO says that it co-optimizes the single largest contingency, which is to limit the generator or interconnections power flow and the primary frequency response or reserve availability. Because it is a market, you don't know how much primary frequency reserve available in the market. If it is so much, you can buy it all. Even if it is expensive, you can still buy it. But if there is a scarcity on primary frequency reserve, then you can't buy it anyway. then you need to limit the contingency size. ELCOT, the US says inertia with sufficient time for fast frequency response before it hits UFLS. It is actually the definitions that inertia will use very often. It means that we know that there is some kind of hero saving us, just like the fast frequency reserve. But there is inertia. There must be inertia that can sustain until they come to save us. So their way is to determine the PFR on the expected inertia and also to offer FFR amount, which means that you have got the inertia on grid and you can have some kind of fast frequency reserve. Then I try to calculate the primary frequency reserve to see if I need to open more generator to provide minimum spinning reserve requirement. And the last one is Brazil. Brazil says that they try to limit the exchange up to 40%. I think it's the best way. Another way is to limit the number of units on bar, because just like something abstract, you don't know how to measure the amount of inertia on grid. Even you can measure, no one knows what it means by inertia, or how much inertia, how much system KE that I need to rescue the frequency during the system failure. Of course, you may say that ELCOT or ERGRID tries to do some kind of a monitoring, such that the minimum inertia, the inertia for the critical inertia is still measured and monitored and try not to violate it. But the problem is that the system operator may not know what it means, and they may not know if it is so important or not. It's better to give them some guidance on how much power, especially on HVDC transmissions, or number of generator on bar, some kind of policy written down so that they can follow. That it will be much easier. That the concept can still be activated from planners to operators. So our goal is to avoid cascade tripping, and as you can see, it is a Brazil grid. The vulnerable parts and also the robust parts. Vulnerable parts, you can see that is often the position with generator, or some place that is far away from the system. It's good to have some kind of interconnections. If we could interconnect it, or provide some kind of voltage support, or the reason why it is the most vulnerable part, because it can trip, and once if the generator starts, even it doesn't trip or it is supposed to start, the system will take so much reactive power to build up the field of the generator and starts to have some kind of generations. It means that it takes some kind of support from the grid anyway, and the scarcity will occur locally over there, and it is the weakest one in the grid anyway. So it is better to have some kind of limit on the system, such that the system can still run well without suddenly shutting down all the generators, leaving one strongest behind, because anyway the system will be having so much vulnerable parts in the grid. So as a recap, we have got the inertia power, and it is to arrest the frequency, and we try to have some kind of fast frequency whisper like BESS or HVDC in feed to partially arrest and partially rescue the frequency, and until the largest portions on the PFR with the governor and also the synchronous generator. This is our goal, and is what we worry and what we concern and what the utilities, other utilities would do to administrative limited the grid such that the grid performance and also the stability can be avoided and grid performance will be ensured. So thank you for listening. 8 pages PowerPoint, but it includes so much information, and if there is any problem, feel free to leave any comments behind, or if there is any questions or suggestions that there is some kind of topics that you want to talk about, then just keep the comments here and tell me. Thanks.